All right, well, welcome to the last day of Math 106, Calc 2. Oh, it's the last day. Yeah, it's the last day. We finally made it. A couple of things before we get into what's going to happen today, I just want to remind you about. So first and foremost, the final exam is on Wednesday. It's Wednesday morning. If you need adjustment on times or something, please let me know, including those of you who regularly have timing issues. Please confirm them with me because I want to make sure everything is set up so that we don't have any hiccups on Wednesday. So go ahead and just send me a message if that applies to you. Also, remember that the final exam is optional if you've done all the homework assignments and gotten a score of at least 50% on each one. All right. That does not include 4.5. I've mentioned this in class. I sent out a message to the entire Canvas group. I still keep getting questions about it. So let me reiterate. 4.5, you do not have to do. I just can't turn it off because some people had already started doing it before I decided to turn it off, to not include it. Okay, so you do not have to do 4.5. It does not count towards your grade. It does not count towards the dropping of the final exam. It does not count, does not count, does not count. Don't do 4.5. Okay, so 4.5, don't worry about it. You can do it if you want. We didn't talk about that topic. I don't want you to spend time on it, but if you are so inclined, please feel free, but it doesn't count towards anything. All right, so I know it shows up on the Canvas site. Does not count towards your grade. You do not need to do 4.5. Okay, so 4.5 doesn't count towards that, but if you are one of those people that have done all the homework and at least 50% and you do not want to take the final, that's totally cool. Please let me know. Yeah, actually, Rigney, you do have to do 4.5. Everybody else doesn't. All right, so just let me know, please, if you're not going to take the final. Just makes life easier for me, so I'm not like, oh, what the heck, right? Why didn't Rigney take the final? Something wrong. If I've already got that message from you saying, yep, I'm not taking the final, I'm like, okay, cool, Rigney's not taking the final. So just do me a favor, send me a message, email, something, letting me know your plans regarding that. How about, I'll say by 5 o'clock, they'll be done for sure. All right, probably sooner. Anyway, that way you've got all the information you need to make your decision regarding whether or not to take the final. Okay, so just wanted to get that out there. I'm going to mention it again at the end just because. So my plan is really to turn it over to you to find out what you guys want to talk about and all that. I imagine we'll start like normal with questions on homework because there are some homeworks due tonight. And then probably what I'll do, just a real quick kind of recap of all the stuff that we talked about. And then I'll just kind of turn it off over to you guys and say, hey, what of these topics should we look at and review? So, but let's start with homework. Are there any questions on the homework sets that are due tonight, the ones from chapter 4, not including 4.5? All right. Got all kinds of good ones popping up here. Let me go ahead and write these down. So errors, let's see, 4.3, numbers 2, 8, 11, and 12, but we don't have to do all of them. Okay, and Vanessa seconded number 8. So we'll for sure look at number 8 from 4.3. Oh, yeah, Lexi's got a vote for that as well. And then from 4.4, Vanessa put on here 6, 10, and 12. All right. Any others? And I apologize, I keep muting. I got a little bit of a cough, so I'll do my best not to cough into your ears. All right, well, let's go take a peek at those. Uh-oh. It just said, wouldn't let me screen share. Let me try this again. There it is. All right. So let's go take a look at the ones from 4.3 first. All right. So, and I'll tell you what we're going to do, at least with these four. We'll go all the way through a couple of them for sure, at least number 8, since that was a really popular request. But we'll at least get them all separated. All right. So how about we'll at least do that much so that you guys can see the algebra necessary to get us to separation, because then it's, you know, a matter of just doing the integral. Unless the integral looks kind of gnarly, we'll jump back and do that. All right, so here we go. We got a separable differential equation, du dt equals e to the t 2u plus 2t. That one's difficult to say this morning. And then we have an initial condition of u of 0 equals 10. All right, well, let me share my whiteboard. And we'll go take a look at that guy. All right, so we've got du dt equals e to the 2u plus 2t. All right, so in order to separate this, obviously moving the dt is going to be easy, but we got to do something with this e to the 2u. All right, well, the algebra trick for this one is to recognize that the addition of exponents is exactly the same as multiplying. So e to the 2u plus 2t is the same as e to the 2u times e to the 2t, right? Remember your rules of exponents. When you multiply, you add exponents together. I'm just going backwards on that. So if I want to then separate, it's going to bring us here. I just divide the e to the 2u, bring that over here, bring the dt up above. And now we're ready to go. The one other thing I'm going to recommend is that you make this a e to the minus 2u, because it might be a little bit easier to see what to do. But then we're going to integrate. All right, so let's see, Ayers, this was on your list. Is this far enough for you? Was the issue beyond after this, or are we good? You're good? Okay. So now that we got it separated, do your thing. All right, so that was number 2. So now let's go take a look at number 8, and this one will go all the way through. All right, so let's see, we've got dx dt equals x squared plus 1 over 16. And then we've got x of 0 is equal to minus 3. All right, so before I go too far into this, because I know everybody's might look a little bit different, is this close enough form to your specific 8s that it's going to be a good one? And I'm specifically asking those that ask about it, Eras, Vanessa, and Alexi. Does this one look good? Okay, cool. So let me go ahead then and jump back to the whiteboard, and let's take care of this guy. All right, so for this one, we've got dx dt is equal to x squared plus 1 over 16, right? And then again, x of 0 equals minus 3. All right, so let's take this one all the way through so that we can actually find our particular solution for this initial value problem. All right, so first things first, let's separate. We're going to get dx over x squared plus 1 over 16 equals dt. So you might be saying, but wait a minute, Bruce, that's weird. Like, why'd you just divide all that stuff? Well, because of the fact that there's an addition, my only options, I got to get x squared to the other side, right? And I can subtract it, or I can divide it. And if I subtract it, the problem is when I multiply by dt, to bring that over here, there would be a dt attached to it from distribution. Let me actually do this. Let me start by multiplying the dt. And it ends up being kind of clear why you got to do what I just did. So let's multiply both sides by dt. So we get x squared plus 1 over 16 times dt. And so to get this x squared onto the other side, I have to either distribute. Distributing is a problem because then I've got a t attached to my x's, and I'm not going to be able to split them apart. So instead, I'm just going to divide by that entire factor. So we'll have dx over x squared plus 1 over 16 equals dt. And in general, I'll just give you this as a, you can always do this. If you've got, for your derivative, if the other side is equal to a function of the independent or the dependent variable, which in this case is the x, you can always just divide by that entire side. Whew. Okay. So now I'm going to multiply by 16 just to get rid of that fraction inside the fraction. So I'm going to get 16 over 16x squared plus 1 dx. Let me go ahead and show you what I did right there. This is the classic multiply by 1. And I did that just so that I could get rid of that fraction inside the denominator. All right, so that's pretty much all the algebra to get us so that we're separated and ready to go. And now we get to have fun and integrate both sides. So the right-hand side is going to be super easy. That's just going to be t plus c. The left-hand side, not so much. Oof, what are we going to do over there? Any ideas, thoughts, suggestions? I definitely like usub. Eric's just put in the chat box. Usub's going to work for us. Depending upon what u we choose, it can be a little bit easier or more difficult. I would pick u equals 4x. Because then du is 4 dx, which is going to make this 4 over u squared plus 1 du. And that's just going to be an inverse tangent form. So that's the substitution I would do. Another substitution that would totally work is trig sub, because we have a sum of squares, where you let tangent of theta equal 4x. So this becomes tangent squared plus 1, which becomes a secant squared, and yada, yada, yada. But I think u sub is going to be a little bit easier. All right, so this is going to give us 4 inverse tangents of u, so for inverse tangent of 4x, is equal to t plus c. So I didn't show the u piece and then substitute back in the u, but hopefully you guys are all cool with what I just did there. All right, so now we get to plug in our initial condition. So if we take these and plug them in, the 0 is going to go in for t, and the -3 is going to go in for x. So we get 4 inverse tangent of -12 equals 0 plus c. So c is 4 inverse tangents of -12. That is not a nice number. It's not one of our nice angles or anything, so I'm just going to leave it like that. So our solution then is 4 inverse tangent of 4x is equal to t plus 4 inverse tangent of -12. All right, so let me just go back and see what it's asking us if we have to solve it for x. Oh, we do have to solve it for x. Lovely. All right, they want it as x equals. All right, well, let's solve this thing for x. So I'm going to divide by 4. I get tangent inverse of 4x is equal to t over 4 plus tangent inverse of -12. To get rid of this inverse tangent, I just take a tangent of both sides. So I got 4x is equal to the tangent of t over 4 plus tangent inverse of 12. And then I just divide by 1/4. So x is equal to 1/4. Tangent of t over 4 plus tangent inverse of -12. And I would say let's just put a box around that because we've got our answer. Obviously, there are things we can do with it, like we could use the sum of angles identity for tangent. That would actually get rid of these tangent of tangent inverse things. But yeah, I say we just leave it here. All right, so okay for that one. And if for some reason the computer doesn't like an answer in this form, just fire me a message and I'll look at yours. And if you have something equivalent to what the calculator or computer is saying should be the answer, I will give you the credit. And that does happen a lot actually with trig functions where the computer wants a specific form and there are, a bajillion alternative forms. So. All right, so any other questions on 8? So remember this trick. This is really useful. If nothing else, just divide by that whole side to move it over. All right, so let's jump back in there to 4.3 because there were also questions about 11 and 12. And like I said, I'll at least get us to the point. All right, good old word problem. Is 12 another one of these? Similar. Okay. So a tank contains 100 kilograms of salt and 2,000 liters of water. A solution of a concentration of 0.025 kilograms per salt per liter enters the tank at a rate of 6 liters per minute. The solution is mixed and drains from the tank at the same rate. And we want to find the concentration of our solution in the tank initially, the amount of salt in the tank after 4.5 hours, and what happens as we go towards infinity. All right, so let's go ahead and see if we can solve this. My recommendation with this kind of problem, and actually this is my recommendation with any kind of word problem, is to draw a picture. And then what we can do is sort of figure out a differential equation for this that we can then solve. All right, so let me go ahead and pull back up the whiteboard. We'll go ahead and clear these, make some new room. All right, so here's my picture. I've got a tank. In that tank is salt water. All right, so we got salt water in here. Yeah. And we have water that's coming in. And we have water that's leaving. And the water that's coming in, we know what rate it's coming in, but we know that whatever rate it's coming in is what's coming out. So here's my little picture. And so let's start looking for or setting up an equation for what we're looking for. And if you go back and you look at that problem, it said it wanted us to calculate. In fact, let me pull it back up so you can see. We want to know about concentrations, right? What is the concentration of our solution initially? How much salt is in there after 4.5 hours? Find the concentration as time approaches infinity. So what we really want is some sort of an equation for concentration. Okay, so what I'm going to do is I'm just going to let Q equal my concentration of salt. So I'm going to use Q instead of C. I don't want to use C for concentration because we use C for other things. And I definitely don't want to use S because my S's look like 5s. So I'm going to use a Q for concentration. Plus, that's kind of standard, by the way. All right, so Q is my concentration of salt. All right, so let's think about initially what we know about it. Well, we're told that we have 100 kilograms of salt, and there are 2,000 liters of water. So the initial concentration is 1/20th kilogram per liter, or 0.05 kilograms per liter. All right, so that's how salty that water is. For every liter, there's 0.05 kilograms. So there was the answer to the first part. What's our initial concentration? But now we need to get to the, well, what's our concentration later? And to do that, we need to know how it changes. So let's see if we can set up a Q prime kind of deal. So let's think about how our concentration changes. We're going to have salt water coming in. And we have whatever mixture in here leaving. So I'm going to write this just generically as in minus out. Okay, so Q prime, the change in my concentration, it's just going to be whatever is coming in minus whatever's coming out. All right, so let's break this down. In terms of what's coming in, I know that it's got 0.025 kilograms per liter, but it's flowing in at 6 liters per minute. So if we were going to break this down into words, this first one is the concentration, right? That's the salt concentration of what's coming in. And then this is the rate at which it's coming in. So in terms of how much salt is coming in. It's coming in at this rate. Okay, so what is that? 6 times 0.025, 12, 15. So I think that's 0.15 kilograms per meter. Or kilograms per minute, I should say. So every minute we're gaining 0.15 kilograms of salt. All right, so then how much are we losing? Well, we're going to be losing whatever the concentration is inside the tank times the rate at which it's flowing out. So I still want to do concentration times rate. It's just now my concentration is Q. And the rate that it's flowing out is, again, 6 L per minute. 6 liters per minute. Okay, now, I want to back up because we have a slight issue here if we just run with what we've got right now. I want you to look at the units here for what's coming in. I'm getting kilograms per minute. So what I really have is the rate of change in not the concentration, but just the amount of salt. Right? It's kilograms per minute, not kilograms per liter per minute. So if I want to use this, and I do want to use this, but if I want to use this, my Q isn't actually the concentration of salt. My Q has to be the amount of salt. Again, look at the units here. Q prime, it's a rate of change. It's mass per time. So that mass is my amount of salt. So we're going to change that. Instead of Q being the concentration, it's going to be the amount, which means my Q of 0, cross this stuff off. If we change it to it's our amount of salt, then Q of 0 is 100 kilograms. But we still have the initial concentration. It's still that 100 kilograms per 2,000 liters. So we didn't actually change anything in terms of our initial concentration. We're just reframing how we want Q to be. All right, so if Q is the amount of salt in the tank, I need a concentration here. So I need to get this as an amount of salt per liter. And so to take care of that, I'm going to divide by 2,000 liters so that I still have concentration times rate. I'm basically making sure that my units match up. That I'm still going to get kilograms per minute. So 6 over 2,000, that reduces down to 3 over 1,000, or 0.003 times Q. Again, that's kilograms per minute. All right, so what we just built actually is our differential equation. I've got Q prime equals 0.15 minus 0.003 Q. And so this one is separable. Think of this as dq dt. I can separate this kind of like we did that other guy. Just divide by that whole piece. And now it's integrate like normal. So the great bulk of the work was done here in creating the differential equation. And it really was looking at what comes in minus what goes out. I call this a pond problem because the traditional way to look at it is it's a pond that's got stuff coming in and going out. But really just think about what we're doing. We're looking at the rate of change. How is the concentration changing? How is the amount of salt changing? Well, it's how much is coming in minus how much is going out. And you can always build them this way. If you take concentration times rate, that will tell you the change in the actual quantity of that stuff. In this case, it's salt. But it could be a pollutant. It could be, you name it. And then, of course, once we integrate this, we're going to get a plus C. But that's where you use this, right? Because we've got, we know how much salt was there at the beginning. So you can plug 0 in for T and 100 in for Q. Use that to find your C. And then once you have your C, that's how you can answer the second parts of this question. So let's go ahead and we'll work this one all the way out. So when we integrate this thing, again, it's going to give us a natural log. So we're going to get minus natural log of 0.15 minus 0.003Q. And all that's going to be divided by 0.003. And that's going to equal T plus C. So I did a U sub. I let the whole denominator equal U. The du gives me the minus divided by 0.003. And then 1 over u gives me natural log. So at this point, let's get our C value. So we'll plug in that 100 for my Q. So natural log is 0.15 minus 0.003 times 100 divided by 0.003 equals 0 plus C. So C is just going to equal whatever this is. We'll just go ahead and kind of leave it like that. No. Here's what we're going to do. Let's do some algebra on this first. Let's solve it for Q. So multiply by the minus 0.003 to get natural log of 0.15 minus 0.003Q equals minus 0.003T plus C. Hopefully you can still see that plus C. And then I'm going to use E to get rid of that natural log. So I have 0.15 minus 0.003Q equals E to the minus 0.003T plus C. And then come back over here. So if I kind of move things around, I get 0.15 minus c e to the minus 0.003t equals 0.003q. So I just traded those places and I made the e to the c come out front as a c. And then lastly, I'm going to divide by 0.003. So let's see, 0.15, I think that ends up being 50. C divided by something is still an arbitrary C. So if I did all that algebra correctly, and I hope I did, this is what Q equals. And now I think this is easier if we, at this point, plug in our values for Q and T. So to get that C, we're going to let T equal 0, and Q was not 200, it was 100. All right, well, e to the 0, of course, is 1. So we get 50 minus c equals 100. So c is equal to negative 50. And again, if I did all that algebra correctly, which I'm not feeling terribly confident in right now. I think this is the equation that tells us how much salt is in the tank. So again, remember what Q was. This was the amount of salt. In kilograms. So at the very beginning, we have 100 kilograms of salt. And as time goes on, the quantity changes according to this. So for the second part of the question, it said something like, what was the concentration at a certain point in time? You plug that T in, this gives you the amount of salt. And if you want to find the concentration, you have to divide by how much there was. So if we wanted a formula for concentration, that was going to be Q divided by how much water is in the tank, which is 2,000 liters. So we could actually do that right here. And you end up with 1 over 40 times 1 plus e to the minus 0.003t. So this formula, again, is our concentration. So two different formulas. One is how much salt's in the tank. The other is the concentration. But you can use either of those to tell you, what happens here. So in terms of part C was what happens as we go to infinity. Well, let t go to infinity. This is going to be e to the minus infinity, which ends up being 0. So as time goes on, the concentration gets closer and closer to 1 over 40. Or alternatively, if we want to see how much salt is in the tank, as time goes on, it approaches 50 kilograms of salt. So it turns out that over time, this becomes less salty. And that's because we're putting in a mixture that's got a lower salt concentration than what we started with. So we end up diluting it over time. All right, so there's this guy. If you look at the book, they work you through these kinds of problems, and they're all the same. They're absolutely all the same. They all come back to the in minus out business. So anyway, are we feeling any better about that? I hope. It's awfully hard to read you guys saying I can't see any of you. But word problems are word problems, right? They're always a challenge because you got to get yourself set up. And for this one, the process is getting yourself set up. Thanks for chiming in there, Hava. I will definitely take a kind of feeling better. That's better than not at all. All right. So let's go take a look at number 12, and then we'll move on to section 4.4. Let me switch windows. All right, so the liquid base of an ice cream has an initial temperature of 85 degrees C before it's placed in a freezer with a constant temperature of minus 19 degrees C. After 1 hour, the temperature of the ice cream base has decreased to 65 degrees C. Use Newton's law of cooling to formulate and solve the initial value problem to determine the temperature of the ice cream 2 hours after it's placed in the freezer. Okay, so we're going to use Newton's law of cooling. Well, here's what we're going to do. Let me just go ahead and pop the book open here real quick. When in doubt, when you go, oh, Newton's law of cooling, I don't know what Newton's law of cooling is. Yeah, go find it. All right, so here's our separable equation section. And if we go down there a bit, oh, hey, look, there was a mixture problem that had a picture that looked a lot like mine. All right, so when in doubt, you can usually go find something. Okay, so here, oh, we just skipped over it. Here's Newton's law of cooling. So let me translate this for you if you're not very good with the reading of the math differential equation stuff. But Newton's law of cooling basically says that the rate of change in your temperature, big T is the temperature of your object, it's proportional to the difference in temperatures of your object and the surroundings, the ambient temperature. So it's actually a pretty easy differential equation. It's T prime equals K times T minus whatever your ambient temperature is. So we're going to use this for our specific example of the ice cream that we're making. And we'll use that to create the differential equation and then solve it. So let's go back. Let me find the right link. I know you guys don't care about what's going on with the Mariners. Just a real quick aside, I'm sure it's kind of funny. I can imagine for you guys, the wide variety of tabs you see in people's browsers when they share them with you guys on Zoom. Yeah, mine are either work involved, music, or baseball. So anyway, all right, so let's go ahead and set this guy up. Let's look at what we've got. So we know that it's initially at 85 degrees C. So that's going to be our initial value. And then it says it's placed in a freezer with a constant temperature of minus 19 degrees C. All right, well, that's our ambient temperature. That's the T sub S that was in that formula. And then this, after 1 hour, the temperature of the ice cream is decreased to 65. We're going to use that to help us figure out what K is, what that constant of proportionality was. So let's go ahead and switch back to a whiteboard. Clear all this garbage. All right, so here's Newton's law of cooling. It always looks like this. So we're going to have T prime is equal to K times T minus whatever our surrounding, our ambient temperature is. So for our specific one, it's T minus negative 19 because our freezer had a temperature of negative 19. So let me just rewrite that. I'll write as the differential as a dt equal to T plus 19. So this guy is separable. I can divide by the t plus 19, gives me a k dt. And now I can integrate both sides. So this gives me the natural log of t plus 19 is equal to kt plus c. I'm going to go ahead and solve it for big T. Might as well. So use the exponentials. I get t plus 19 is equal to e to the kt plus c. So I'm going to write this as minus 19 plus c e to the kt, where that c is a different c. It's e to the c. All right, so there's our solution, our general solution, but now let's get our particular. So we knew that initially the temperature was 85. I think I recall that being the answer. If not, or the value, we're going to run with it. So I'll go ahead and put those in to help me find my C. So I get 85 equals minus 19 plus C e to the k times 0. Well, e to the k times 0, e to the 0, which is 1. So we get 85 equals negative 19 plus c, or c is equal to 104. So we got our c value from the initial condition. And the only thing we don't know is k. But this is where we're going to use that other fact. We were told, I believe, that in 1 hour, the temperature was down to 65. Let me just actually double check that. Let's double check that. Yeah, so after 1 hour, the temperature of the ice cream base had decreased to 65 degrees C. Okay, so T of 1 is equal to 65. So we can plug those numbers in. And this is going to allow us to solve for K. So we'll add 19 to both sides. Gives me 84 equals 104 e to the K. So e to the K is 84 over 104. So K is the natural log of 84 104ths. So whatever that is. So we can put that back in here. And now we've got the formula for the temperature of our ice cream base. It's going to be negative 19 plus 104 e to the natural log of 84 over 104 times t. And now you can plug in your different time values and you'll figure out what the temperature of your object is. So another example of separable. That's just the good old Newton's law of cooling. All right, so that K value, that's all dependent upon the actual material. I'll just give you some physics here. The K is like, what is this object made out of? Things that have a high thermal conductivity, meaning the temperature changes quickly. Those will have a bigger K, or a more negative K, I should say. And yeah, so that's what K is all about. It's just how well does the object transfer energy via heat. And yeah, there you go. So hopefully you know what to do at this point. Plug in 2 for little t. You'll get a big temperature in 2 hours. All right, so basically the moral of the story here is with differential equations, there are so many applications. Like, it's an incredible number of applications. But these are just some of them. Okay, so let's go take a look at 4.4 real quick. And hopefully you guys saw the video. I did post the video. I think maybe that was Thursday night. I put a video up about the logistic equation. And the logistic equation is just another application of differential equations. It's a more realistic form of an equation for population growth because it caps it. It says that there's a maximum number of that your population can be as time goes on. Without that cap, if we just use the simple exponential growth, you would see that your populations go to infinity. And those are not very realistic, right? So let's just take a look at number 6. So number 6, this one says solve for when the population increases the fastest in the threshold logistic equation. Okay, so when does the population increase the fastest? Now, you might be tempted to take this equation and solve it. I do not recommend that. I do not recommend that, although you can. And then you could use that equation to help figure this out. Because let's just think about what we know when a population is increasing the fastest. What does that mean in the calculus world if something's increasing the fastest? And I'll give you a hint. You got to go back to first quarter calculus. Let me help you out. What tells you about how a function is changing? What thing in calculus tells you about how a function changes? All right, thanks, Rigney. The derivative, right? The derivative is a change. Okay, so we know how a function changes by looking at its derivative. And so if we're looking at a population increasing, that means its derivative is positive, right? So we want to figure out what p-value makes it so that we have the fastest increase, which means where is our derivative most positive? So that's what this is actually asking us to do, is just figure out where the derivative is the greatest positive value. All right, now, instead of solving for p and then differentiating, I'm going to use the fact that we already know about the derivative. That's what this thing is right here, right? This is our derivative. So I can actually look at this equation and figure out where it's biggest, and that's going to answer my question. So here's what I suggest we do. I suggest we draw a graph of this equation and see where it's largest. All right, so I'm going to go ahead and just open another window here real quick. And we'll go to Desmos. That's my go-to. Okay, so we want y equals 0.7x times 1 minus x divided by 4,500 times 1 minus 1,500 divided by x. So that's the same formula, just with x's instead of p's. Now, obviously, I can't see anything right now, so let me zoom out. All right, so I'm looking for where it's got a maximum, which on this graph is looking somewhere around 3,000. Right? So looks like it's around p equals 3,000. We get a y prime of 350. All right, so there you go. There is the population at which this is increasing the fastest. Now, if you're looking at this and going, well, what if I don't have a graphing calculator? What if I don't, what if that hadn't been a nice point or whatever? Here's how we could use calculus to figure it out. I want to find the maximum of this function. Well, how do you find the maximum of a function? Again, go back to first quarter. What do you do to find a max? There you go. Thanks, Ragney. Good. You take your derivative, you set it equal to 0, find your critical points, and then you test them. So what we could do is differentiate this just with respect to x and find the critical points. And you'll see that one of them is 3,000. And you can test it using either the first derivative test or the second derivative test. And you would see that it does lead to a maximum. So to answer this one, we didn't even have to calculate p. I have no idea what the equation for p looks like. But that's because all I needed to know was where the derivative was greatest. And they already gave me the equation for the derivative. So don't make more work for you. They already give you what you need. Make use of it. Okay, so that's the trick to this guy. So real quick, let me pop and look at the other ones that were questions about, 10 and 12. So number 10. All right, so populations that can be modeled by the modified logistic equation here can either trend towards extinction or exhibit unbounded growth in finite time, depending on the initial population size. So if B equals 0.01 and A equals 0.3, use phase portrait analysis to determine which of the two limiting behaviors will be exhibited by populations with the indicated initial sizes. Okay, so phase portrait analysis. What the hell does that mean? All right, well, I don't know exactly what phase portrait analysis means because I don't use that term. It's probably something that when I see it, I go, oh, okay, yeah, but I don't call it that. But let me show you how I would do this, because this is another one that we don't actually have to solve for P. We can get a little creative. So let me go ahead and write down this differential equation though. P prime equals P times, and we're going to put in 0.001 for B and 0.3. Attack this problem whiteboard here. Let me go ahead and clear all this stuff so we can start fresh. All right. So let's start here. I've got my P prime equals P times 0.001 P minus 0.3. So here's the very first thing I do actually. I'm going to look and see where does this equal 0. Okay, so I'm going to take this guy and I'm going to set it equal to 0. Now that gives me two possibilities. One is p equals 0. The other is when that other factor equals 0, which I think is 300, if I do the math correctly on that. Okay, so why did I do that? Well, this actually gives me the places where this function have equilibria. I don't know if you remember, but for an equilibrium, this was going to be where your derivative is equal 0. Because if we have that population, it will never change, right? Like if we're at a population of 300, when I plug 300 in, that makes my derivative 0. So the rate of change is 0. Well, if rate of change is 0, your function doesn't change. So that's your p equals 300 and p equals 0. So I know that for those populations, now I'm drawing a slope field. I've got at 0, oops, I've got that, and at 300, got this as well. So the question is what happens when we get on either side of these? Do we go up? Do we go down? What's the deal? Okay, well, let's just start thinking about this. If I were to plug in a number bigger than 0 but less than 300, what's going to happen? Well, think about the two factors. This guy is always going to be positive, right? P is just our population, so it's always going to be positive. This other one is going to be positive or negative, depending upon which side of 300 we're on. If we're bigger than 300, this is going to be positive. If P is less than 300, it's going to be negative. Okay, so let's just think about this again. If we're greater than 300, both of those are positive, which means we have positive rates of change. So for our slope field, we're going to see something that looks like this, right? So it's positive, and it's going to get steeper as we go more up because this number is going to get bigger. All right, now if we're less than 300, this piece is negative times a positive. Negative times positive is negative. So this is going to be pointing downward. It's always going to be pointing downward in here. But it's going to get steeper and then flatten out depending upon where we are. All right, so basically now I know what's going to happen depending on my initial value. If my initial value is greater than 300, like I'm up here, I'm going to just go up and I'm going to grow to infinity. If my initial value is below 300, I'm going to decrease and approach 0. So this is one where the 300, that's an unstable equilibrium, because if we step off of it, we go away from it. The 0 is a stable equilibrium, because if we move off of it, we go back. So let's go back and answer the question. Right? So again, we want to determine which of the limiting behaviors will happen here, right? So it says it either trends towards extinction or exhibits unbounded growth. All right, we saw that. So again, it's all about our initial population. So 375, that was more than 300. And so we know that that's going to grow unbounded. So that's B here, doomsday scenario. If we have fewer than 300, so the 189, we're going to drop towards extinction, which I guess would also be a doomsday scenario. In either case, this would be bad if your population was defined by this differential equation. I mean, it's great if you're at exactly 300, but if you dip below it, you die out. If you go above it, you grow until like there's too many of you and you start dying and whatnot. Like, this is bad news either way. All right, so there are those. And then again here, there's also a constant equilibrium solution. Find this solution. Okay, well, that was the 300. That was the value that's going to keep us always at 300. All right, so then this guy, P of 0 equals 375, that just means solve the differential equation. I'm not going to do that. I'll leave that to you. But that would be take this equation and solve it. Let me at least get it separated for you because this is a separable. So we would have dp over p times 0.001p minus 0.3 equals dt. And now you need to integrate both sides. Whoops, let's put that over there where it belongs. And for this piece on the left, this one you're going to want to use partial fractions. I would recommend multiplying by 1,000 on the top and bottom here, just to make this not quite so terrible. It would look like 1,000 dp over p times p minus 300. I think that's going to be a little bit easier to do partial fractions on, personally. But anyway. So again, integrate both sides, you'll get your solution. And that's how you're going to finish off that problem. So if you saw the video on logistic growth, the idea of logistic growth was creating this carrying capacity. That's where this other factor is coming in. This one, though, it's not a carrying capacity. It's what we call a threshold, so that if you dip below it, you die out. Anyway, hopefully that helps with number 10 here. Okay, so lastly, number 12. Let's just take a peek and see what that's asking us to do. All right, so assume there's a certain population of deer in the forest whose growth is described by the logistic equation. Constant proportionality for this type of deer is 0.47, and the carrying capacity of the forest is 10,000 deer. If the starting population is 6,000 deer, then after one breeding season, the population of the forest is... Okay, so this is one where we want to just use the formula that we derive from the logistic equation. I'm going to save us a little bit of time. I'm not going to rebuild it. If you want to see where this comes from or how to find it, you can either read it in the book or you can watch my video, because I definitely derive it for you. But we're just going to jump to the, kind of get to the important part here. I know that they have the equation here somewhere. There it is. Okay, so, wow, dang it. This is where we want to be. fine motor skills are not here today. Okay, so let's look at this equation right here. So here's what all the different values are. Okay, so P naught, that's your initial population. That's how many you have at the very beginning. K, that's your carrying capacity. All right, and then R is your growth rate. So if we pop back to this problem, right, notice we've got all of this. Our starting population is 6,000 deer. That's going to be P naught. The carrying capacity is 10,000 deer. That's our K. And then the constant of proportionality, they call it little k, that's the one that's R in that formula, 0.47. So back here, you're gonna put 6,000 for P naught, 10,000 for K, and 0.047 for R. Put that into all the respective spots. And that's your formula for how many deer are in there at any given time. So then to finish the question, I think it's at, what was it, in the second year? Oh, then after one breeding season, the population of the forest is, all right, well, so that would be plug in 1 for T. So you plug in your 1 for one breeding season, and you'll know how many deer there are. So it should be more than 6,000, and it should definitely be less than 10,000, because the carrying capacity is a value that we're approaching as we go towards infinity. So I think you should be able to take care of that. That's just a plug and chug, because we actually already did all the work when that equation got derived. Again, I'm going to have you reference the video I made. Go to YouTube and you can see my talk on logistic growth, and you can see exactly where that formula comes from.
I guess my question was on the constant of proportionality. I couldn't figure out what it was, and then I did use it for R, and then I got it wrong. So I think I just maybe made some errors in my calculations. But yeah, okay. Thank you. That helps.
Yeah, no, you're welcome. All right, so cool for that. All right, so I'm going to stop sharing here, but we're almost out of time. So let me just sort of give you here's what you need to do for your final. So I know that probably doesn't apply to a lot of people, but the final is cumulative, right? The final is cumulative. So there's going to be a little bit of everything. But here are the big takeaways from this quarter. Here, you can actually divide this quarter into a couple of chunks. The first one is integration techniques. I mean, that's what this this class has all been about, is integration, right? And so a big part of this class are the integration techniques. So you should know how to do U substitution, integration by parts, trig substitution, partial fractions, right? Know how to do all these different integration techniques. Be able to recognize when they're useful or when you're going to want to try one over the other. And it's all about form, right? When you have a sum or difference of squares, trig subs should start popping in your head. If you've got a fraction, if you've got a rational function, that's when you start thinking partial fractions. If you've got multiplication, hey, that's integration by parts. Or integration by parts is also very useful if you have just one term, right? Because that can be your U. So practice recognizing which integration technique to use. There's often more than one, right? You can actually solve problems using all kinds of different combinations. Like think back to that horrible one on exam 2 where I asked you to do it with trig sub. And most of you are like, no, I want to just use U sub. Yeah, I mean, they both work. So there are lots of different possibilities depending upon what it is. But so that was the first chunk of this class, was what are the integration techniques? Then we did a ton of applications. What are the applications to the integrals? And that's probably the part of this test that you're most concerned about. And there were tons of different applications. We did fluid forces, we did work, we did volumes, we did arc lengths, we did surface areas, right? Things with revolution. I'm sure there are more that I can't, well, in this differential equation section, you can think, if you want to call those applications, right? Newton's law of cooling, population dynamics, oof, it's endless. But how do you know that you're going to do an integral? You're adding something up, right? Integrals are all about adding something up. So it can be something as simple as areas under curves, or it can be something super complicated, like a work problem, but it's always we're adding stuff up. So that was like the second big chunk of this class. And then the third chunk was the differential equations, which really is sort of an application of integration, but it's just a slightly different, I kind of like lump it into its own thing. So on the final, there will be some differential equation things. Definitely something separable. Your books, you've got your notes, so you should be good with, you can reference that. One thing I highly recommend is taking your notes and condensing them a bit, because like if this is your notes, you don't want to be on the final flipping through everything trying to find the one page that's got what you need. So what I would recommend is kind of condense it down and have just a page or two that have the highlights that can give you that initial push towards solving the problem. And then maybe then be able to access the more detailed stuff if you need it later. But that's definitely something I would do if I was taking in, an open note, open book kind of test, because time is still an issue. Obviously, it's not like you've got an infinite amount of time. So a little bit of front loading would help. That's also going to help you kind of notice what you know better, as you're kind of like organizing stuff. You might go, oh man, I do not remember how to do integration by parts. So practice that, right? Use that as a way to help concentrate some of your time in terms of the studying. So a little bit of everything, but the final exam is going to be more top level ideas, not as detail oriented. So I know a lot of you are probably thinking back to specifically exam 2 and going, oh my God, if the finals like that, I'm going to die. It's not going to be like that. It's not. I'm not going to go into as much depth. I'm not going to make you think quite as much about a specific type, because I am well aware that this is a little bit of everything. And I want to see, did you get a little bit of everything through the entire quarter? So it should be more straightforward. I think it's going to be more like, imagine putting all the quizzes together. If you were to take all the quizzes, put them together, well, that's probably going to be a bit long for a final exam, but at least in terms of the ideas of the types of problems and the things that I'm looking for, hopefully you kind of got that the quizzes were more straightforward, more like the homework, more just a, hey, show me, do you know how to solve a separable differential equation? Do you know how to do trig sub? Do you know how to find the arc length, right? So I think instead of concentrating on exams and at least in terms of difficulty of questions, think more like quizzes. That should probably push you in the right direction in terms of what kinds of things to expect on the final exam. Anyway, so yeah, we're kind of out of time, but I will let you know, I do have my office hours today. I have office hours tomorrow. I will be available via email and all that. So please do not hesitate to reach out if you have any questions. And again, just a couple of reminders. If you're not going to take it, please let me know. Obviously, if you just don't show up, you just don't show up. But if I know ahead of time, then I'm not like wondering if you fell off the face of the earth. If you have a different testing time need because of work schedule or whatever else, again, please let me know, and including those of you who we've been doing that kind of thing up to this point. Don't forget to finish the homeworks, not including 4.5 by tonight at midnight. And I will have everything graded by 5 o'clock today for sure at the latest, so that you know exactly where you stand for those of you who have the option of not taking the final. All right, so that's all I've got. Unless there anything, if you guys have anything here for the record, we'll go ahead and call this a day. But it's been real, it's been fun, it's been real fun. And hopefully at some point I will get to see you guys in the real world. All right, so good luck on your finals, and I will see you guys when I see you.